this is not really about Hodge theory. It's about more of the algebraic aspect, which is numerical cycle classes. So we start with notation. X is a projective variety over an algebraically closed field. And we assume that the dimension of X, we denote it by n. Okay, and then for any integer, one has the numerical groups of X. So I always work with R coefficients. And then maybe it's worth recalling the definition, because in the singular case, it's not what most people expect. Okay, so let's define what it means for a k-cycle to be numerically trivial. So Z is numerically trivial, and it's a k-cycle if the degree, if whenever we intersect it with Chern classes, we get 0. So Z has a Chow class. Chern classes of vector bundles act on Chow groups. If we ask that this is a Chern polynomial of weight k, then the result is going to be a degree 0 Chow cycle. And because X is projective, because it's proper, we have a degree map which counts points. So this is the definition. If X is smooth, then this coincides with the classical definition, which just means intersect Z with something of complementary dimension. And if you always get 0, then you're fine. But the equivalence between the definition is some form of Riemann-Roch. OK, so what do we know about these guys? We know that they are finite dimensional. It's also useful to look at their duals. And where these guys are classes of cycles, if you look at this definition, you can think of elements here as classes of Chern polynomials. OK. So for example, if k is equal to 1, then n upper 1x is the numerical group of Cartier divisors, not Weil divisors. And n lower 1 is, you recognize it as the usual numerical group of curves. So what is positivity? What are positive cones? So inside nkx, you can look at the pseudoeffective cone. So this is the closure of the cone of effective k-cycles. And inside the dual vector space, you can look at the dual cone. OK, so what are some examples? So the classical case is codimension 1 or dimension 1. So in this case, Lehmann tells us he tells us that the Neff cone, so this is the closure of the ample cone. So in particular, at least on a smooth variety, you can think that any Neff class is pseudo-effective. And also Kleiman's result tells us why it's interesting to look at pseudo-effective classes. It tells us that to test that something is, so Kleiman's result actually says that the ample cone is the interior of this cone. So then we find why it's interesting to look at pseudo-effective classes. To test that a divisor class is ample, we have to check that it's positive on all pseudo-effective curves. It's not enough to look at effective curves. And actually, there is a result of an example of Mumford. So he shows that there exists X a rule surface and Xi an F class with the property that the self-intersection is 0, but whenever we intersect it with an irreducible curve, we get a positive number. You can show a little more here. You can show that Xi, M Xi, is not numerically equivalent to any effective curve. So this is for all m. Maybe it doesn't say much. If I use numerical equivalence to put the m here, if you think of R or Q divisors. But yeah, you get the point. Okay. So that's the classical setting. What can we say about some examples in higher codimension? So it's standard here to look at toric varieties. Then we can compute that these guys are polyhedral. They're actually equal to the effective cones. So they're polyhedral, generated by T invariant subvarieties. If X is smooth, then Qifeng Li. So he shows that an inclusion that I mentioned before of Neff classes in pseudoeffective classes still holds. So we have that Neff classes are pseudoeffective. Smooth and toric, of course. So this is for all k, not just for k equal 1. Okay, these are toric varieties. So maybe a few examples create the illusion that Neff classes are always pseudo-effective, but then relatively recent work by Debar, Ein, Lazarsfeld, and Voisin. So they show that there exists X, which is a self-product of an abelian surface. And such that the Neff cone in codimension 2 actually strictly contains the pseudo-effective cone. So in particular, the naive intuition of the case k equal 1 does not hold. Or you can think that there is no Kleiman result because the Neff cone cannot be generated by classes of subvarieties or of effective cycles. So maybe you're a bit confused by the fact that I'm talking about inclusions like this, which would seem that I'm mixing apples with oranges. So this guy lives in codimension 2 numerical classes. These are dimension 2 numerical classes, but in the smooth case, because I'm on a fourfold, those are basically the same space. Yes, an homogeneous variety. Yeah. Yeah. Any questions?
No, but can you just repeat the question?
From codimension to dimension? Okay, so I have this definition for numerical equivalence. In the smooth case, it coincides with the usual one. Okay, in that case, n upper k is isomorphic to n lower n minus k. So the usual definition of numerical equivalence is you intersect with cycles of. So let's put this. So if you're on a projective manifold, so this statement does not depend on the Hodge conjecture. If X is smooth projective, and this is because you have the intersection pairing in the smooth case.
Yeah, but we're using the duality.
Okay, other examples. So I computed what happens for projective bundles over curves. And while I don't want to give the precise result of the computation, I will say that the pseudo-effective cones and the NEF cones are determined by the numerical data in a Harder-Narasimhan filtration of E. So you have a filtration of E with semi-stable successive quotients, and these quotients have some ranks and some degrees. Those together are the numerical data. And you can use those numbers to compute these cones. Okay. An easy example that's particularly useful for us today is that of a Grassmann variety. So let's say this is. No. You can show that the NEF cones are contained in the pseudo-effective cones. They are equal if E is semi-stable. And the NEF cones are also closed under products in this case. In this case, they're also not closed under products, which was a previous question an old question by Grothendieck. Okay, so let's say X is G, which is a Grassmann variety. Then we have that the pseudo-effective cone, the effective cone is equal to the pseudo-effective cone, is equal to the NEF cone. And these are generated by the non-zero Schubert cycles. Of dimension K. And they're actually simplicial cones in this case. Okay. The toric thing is true for any spherical variety. So for toric varieties, we don't have equality here between the NEF cone and the pseudo-effective cone. We just have an inclusion. Grassmann varieties are better. Okay, now let's see. What can we say about these cones in general? So let's put some easy remarks. So of course, the effective cone generates the numerical group. If I have ample classes, I can look at the complete intersection. And this is actually going to be in the interior of the pseudoeffective group. Okay, if we have a morphism, so the numerical groups in lower k, they're covariant objects. We have push forwards, like we have for homology. And this preserves pseudoeffectivity. So these are, like I said, easy statements. And furthermore, if pi is surjective, then the inclusion is dense. Actually, we have equality if we look at effective cones, not at pseudo-effective cones. I'm going to also show that we have equality, that this dense inclusion is an equality. But it's interesting because the image of a closed cone through a linear map is not always closed. So that's the statement that hides here. Okay. Again, if I have a bunch of ample classes, let's take a bunch of nef classes, then their intersection is nef. Okay, these are my easy remarks for today. So this is interesting for the nef cones because I said that in higher codimension, the product of two nef classes may fail to be nef. But in codimension 1, things are fine, essentially due to Kleiman. Okay. Now let's try to say something non-trivial. In the strict interior of the nef cone. Wait, no, it's nef. Actually, it's in the strict interior of the nef cone. There is something else that I can't show about it. I can't show that it's pseudo-effective. Yes. Yeah. Okay. So let's take now a bunch of ample classes. Well, let's take just one. Okay, then the statement is that h to the k, this complete intersection, belongs to the strict interior. Of the nef cone. So a consequence of this, in particular, so I have the nef cone lives inside a vector space, lives inside an upper K, inside the numerical dual groups, and I'm saying that it has non-empty interior there. So I could look at the half line inside R2 that has empty strict interior. So the statement here is that the nef cone generates an upper K, which might not be a trivial statement. We'll see. So in part, yes, yes. So this is what I was going to say now. In particular, the nef cone generates an upper Kx. And when that happens, it's dual, which is the pseudo-effective cone. So this further implies that the pseudo-effective cone is pointed, or some people call it strict, some people call it salient. And what it means is that plus minus alpha pseudoeffective implies that alpha is 0. Okay. So we have a problem with this, which is that we don't know that the Neff cone generates an upper K x. So we would like to first construct many examples of Neff classes. And we have here a suggested set of examples, which is complete intersections of Neff classes. Then the question is that enough? And the answer is no. So example, if you take x to be G24, then this dimension is 1, and this dimension is 2. So you have only one dimension worth of complete intersections, which means that the Neff classes, which are complete intersections, do not generate an upper 2x. So we have to come up with more. And the idea here is to look at the correct the definition of the numerical equivalence that I raised, which was stated in terms of Chern polynomials using vector bundles. And the idea is to use vector bundles. So when you talk about vector bundles and about positivity for vector bundles, you have several notions that suggest themselves, such as global generation, Neffness, and dampleness, if you know what those are. But the easiest one to work with is global generation. So we make the following definition. So this is the Pliant cone. So this is the closure of cone generated by weight k monomials in Schur classes of globally generated vector bundles. By numerically effective, do you mean Neff? So no. Yes, I don't think I can. So the problem is that a priori you don't know that you don't have pseudo-effective classes that have zero intersection with the complete intersection. So I know you know that over C, but I'm working in arbitrary characteristics. So that's something that we want to do. So of course it's true if you look at effective classes, but limits of effective classes could ruin things. Okay, so what's a Schur class? So Schur classes are sort of like Chern classes, but they're associated to partitions, not to integers. So if we have lambda partition of K, then and the vector bundle E, to this data we associate S lambda E, which is a determinantal formula in Chern classes. So ij going from 1 to k, I guess, in this case. So a particular case, when you have lambda just the partition K itself, then you recover the Chern class. Yes. It's the Segre class of its dual, if you look at Fulton's definition of Segre classes. Okay, so we have this definition with vector bundles. There is another definition which is more geometric. So equivalently, so this is generated yes. Yes. Okay. Movable does not imply nef, I think. Depends what you mean by movable. If do you want them to move to cover, or do you want them to move to be in general position with respect to any subvariety? Can you show that? So if you look at cohomology, if you look at the nef cone in cohomology, then this statement is easy in characteristic 0. It has an analytic proof with currents. It's in your paper with the Bar and Jiang. So I'll present a proof that I understand. So like I said, I'll show you a proof that I know and understand. So the Pliant cone is the closed cone generated by pulling back effective classes and product of Grossman varieties, where gamma ranges through morphisms from X to products of Grossman varieties, finitely many Grossman varieties. And you can figure out that the relation between that is Schubert cycles are sure classes of the tautological quotient bundle on each step here, and when I pull back monomials, I want to look at products of Grossman varieties. And these maps, gamma, will be Gauss maps constructed from globally generated vector bundles. Okay, so you have this geometric definition if you prefer it. So let's see. What are some easy examples? There is only one easy example. Well, examples. If the codimension is 1, then the Pliant cone coincides with the nef cone. So this is because they're both the closure of the cone generated by first Chern classes of globally generated vector bundles. So what's another example that I can do? I can compute the Pliant cones for Grossman varieties, and they actually coincide with the nef cone. And like I said, also with the effective cone. Yes. So the Schubert classes are sure classes. That's the content. And this is about, these are the only examples that I can compute. Basically, I can do some simple projective bundles over P1, and that's about it. But the thing with these classes is that maybe they're not that interesting to compute, but they're useful for proving this. Yes. Like I said, those are the only examples where I can compute it. In general, it seems hard to construct interesting globally generated vector bundles without twisting by a high power, which sends the Chern classes too far. Okay, so what can we say about these? So the Pliant cone generates an uppercase x. So this is because in the Pliant cone, I'm looking at monomials in Schur classes, which contain monomial in Chern classes. But I'm only looking at globally generated vector bundles. On the other hand, on projective varieties, I have many globally generated vector bundles by twisting with a large ample line bundle. So I think that the point of that was to study positive polynomials of degree n, of weight n. So points, but point classes, and they show that if you look at the polynomials that are positive for ample vector bundles, then you basically get this cone. Yes. But I'm not looking just at codimension n. I'm looking at all codimensions. Okay. So these are also NEF. So in arbitrary codimension, I don't know if you get the same thing if you replace globally generated by NEF or ample, because you don't know if Chern classes are pseudo-effective. Okay, so this generates an upper K, and they have a yes. So this is closed under product. That's because I look at monomials. It's not very interesting. So something that was proved by Fulger and Lazarsfeld in the paper that Claire is mentioning. Is that the Pliant cone is contained in the intersection of the NEF cone, and if you can make sense of it, also in the pseudo-effective cone. So if you take a Pliant class and pair it with the fundamental class of X, you get something pseudo-effective. Okay, in particular, we have this inclusion. So this is due to Fulger and Lazarsfeld. It's not that hard if you look at the second interpretation, because I'm pulling back effective classes from a homogeneous variety, and the statement is that actually this is the interesting inclusion. If you pull back something effective on a homogeneous variety, you're going to get something pseudo-effective, and because you can restrict, like Claire said, you also show that it's NEF. Okay, So the first and third remarks show that the Neff cone generates an upper kx. And also that we can all talk about the strict interior of the Pliant cone. So when Brian and I introduced it, we wanted to call it the flexible cone so that we can denote FL to sneak our initials in there. But we figured out that the notation was already taken. There is a notion of flexibility actually for some Schubert cycles and Grossmannians. It was studied by Izet and one of his co-authors. Okay, but what we actually want to show. So my favorite cone defined in terms of intersection theory, which is the universally pseudoeffective cone. So this is in n upper kx. So this is the set of all classes with the property such that for any morphism pi from y to x, we have that the pullback of alpha intersected with the fundamental class of y is pseudoeffective. And then you can show that you have an inclusion. I mean, what I said, basically because global generation is preserved by pullbacks, you get that the Pliant cone is contained inside the universally pseudoeffective cone using this inclusion, Pliant inside pseudoeffective. So we have Pliant inside universally pseudoeffective inside the Neff cone. If you want to intersect with the pseudoeffective cone. I know that this definition may fail. So this definition may fail because of the Barra and Lazarcel example. I don't know if this definition fails. If this includes this inclusion, equality may fail, yes. So equality may fail here, and we don't know what happens here. Okay, and for the universally pseudoeffective cone, you have that the product is universally pseudoeffective and all those properties. What?
What kind of map is that?
Any map. Well, map from a projective variety.
No?
Definitely not. So if you put surjective, then you have that the pullback of a pseudoeffective divisor is pseudoeffective, but you want to get Neff. You want to get Neff. It's actually enough to look at maps that are generically finite onto their image, but the image doesn't have to be the entire X. Okay, so now I'm going to prove this theorem that I'm erasing. Okay, so we're actually going to show that the complete intersection actually belongs to the strict interior, which in this case is the interior of the Pliant cone. Okay, so how are we going to show that? So we know that the Pliant cone is full dimensional, so then we can choose finitely many vector bundles that are globally generated. Such that the Chern monomials so monomials of weight k in Chern classes of these. So such that these generate an upper kx. So I'm using just Chern classes here, not Schur classes. So I can do this because of the definition of numerical equivalence. And Chern classes are particular cases of Schur classes, but the Cherns are enough in this case. It's just that if in the definition of the Pliant cone I just use Chern classes, I wouldn't be exactly sure I know how to prove such a statement, because I don't know if this is true on Grassmannians, that if you just use Chern classes, you get all Schur classes. It's definitely not enough to look just at the tautological quotient bundle, but you could look at more things. OK. So now let's put P, which is the sum of all these monomials. Now, the claim is that because the monomials generate an upper K, and they are pliant because the Chern classes are Schur classes, that this thing belongs to the interior of the Pliant cone. So you add the basis of positive things, you get an interior basis, and you get an interior thing. So now let's put P prime. So this is sum of same monomials. But replace each EI by the sum of all of them. So let's call this guy E. OK, so now let's see what happens. Because again, I'm using Chern classes, and we know what happens when you look at the Chern class of a direct sum. When you expand this out, you'll see that what you get is P plus sum of other monomials. It's more like more monomials than others. OK, so again, I'm just adding more monomials to P, which was interior, and I'm using Chern classes of the EIs, which are globally generated. Hope I mentioned that. So then the result is again going to be in the interior of the Pliant cone. If you have a cone and add a class that's in the cone with a class that's in the interior, you get something in the interior. OK, but now the benefit is that P prime only depends on one E. So there exists gamma from X to one Grassmann variety. So this is the Gauss map of E. So this is generated by some vector space of sections, and I'm sending a point to the quotient that each fiber of E is. OK. So now, because that P only depends on E, we have that there exists alpha in the pseudo-effective cone of codimension K. So let me use this notation, although I didn't actually define it, such that P prime, is the pullback of alpha. And this belongs to the interior of the Pliant cone. OK. This implies actually that if I look at the pullback through gamma of the entire pseudo-effective cone or effective cone, and I look at the relative interior, it implies that this is contained inside the interior of the Pliant cone. So I have a cone that's I know that this guy here coincides with the Pliant cone of G. So when I pull it back through gamma, I obviously get something in the Pliant cone of X. But I know that this cone, when I pull it back, contains an interior class here. So that implies that the entire interior is mapped to the interior of this. The entire relative interior, because it may have smaller dimension. Yeah. Okay, but the Pliant cone here coincides with the pseudoeffective cone, and I said that the complete intersection classes are in the interior of the pseudoeffective cone. So let A in, let's call it amp 1G. Then A to the K belongs to the interior. Of the pseudoeffective cone of G. But this, in this case, this coincides with the Pliant cone of G. So then we get that the pullback of A to the power K belongs to the interior of the Pliant cone of X. Okay, so now we're in pretty good shape. So we don't really know that the pullback of A is ample. We only know that it's nef. But the claim is that this is enough. So because A is ample, the pullback is nef. So there exists some large n such that H minus 1 over n pullback of A is actually ample on X. So then when you compute H to the K, you're going to get the pullback of A to the K plus sum of complete intersections plus sum of intersections of nef divisors. But intersections of nef divisors are pliant. I hope I mentioned this. So nef divisors are limits of globally generated line bundles, and if you look at a product of Chern classes of this, that's a monomial in Chern classes of globally generated line bundles, and because in the Pliant cone I allowed limits, this is fine. So I'm adding an interior class again to a Pliant class. So H to the K is in the interior of the Pliant cone. Okay. I don't know if it's the same thing. Yes. Yes. So in here at the end, I could change E by twisting it by something, by a high thing, by a high multiple of an ample thing, and that would actually show that that the pullback, that the Gauss map is finite. So the pullback is ample. So maybe that could shortchange some steps. That the intersection of nef things. So nef things are limits of globally generated line bundles. And intersections of globally generated things are pliant. So the limits also work. Okay, so what are some corollaries of this theorem? So this would be a restatement of actually the theorem. So if I define the degree with respect to H of a class alpha as being H to the K times alpha, where let's say here alpha is pseudo-effective, then this function extends to a norm on an upper Kx. so not linearly, but it extends from the pseudoeffective cone. This is because I know HK is in the interior of the dual of this guy. So this interpretation turns out to be useful for some geometric statements, like the one that I promised in the beginning. So let's say pi from x to y is surjective. Then actually we have that the push forward of the pseudoeffective cone is equal to the pseudoeffective cone of y. So the improvement is that the pseudoeffective classes here, which are not effective, are also covered. So the way you do this is you write a pseudoeffective class as a limit of effective things. You construct preimages for each effective thing, and you do some work to show that the degree is bounded. And that extends to some norm, so they're bounded in a norm, so they converge to something. So I don't have that much time left to do something new. So I'll say that this was mostly foundational work to try to say what can one say about positivity in higher codimension. So I was trying to see to what extent that Kleiman's criterion extend. To what extent does Kleiman's criterion extend? And what we have is one of the easy implications there. So Kleiman's criterion says that the interior of the Neff cone is the ample cone, and I'm showing that that complete intersections are in the interior of the Neff cone. And Brian and I, so we use this as foundational work. We defined, the title was positive cones. We defined more. So I showed you the universally pseudoeffective. There is a movable cone of cycles, which sort of which wants to say that a cycle is movable if it deforms in a family that covers X and without some sort of fixed loci. And we use that to show that Zariski decompositions exist for all cycles on projective varieties. So you have to make a choice in what you're asking for. So we show that for any alpha pseudoeffective, there exists a writing, a decomposition alpha is equal to p plus n, where p is movable, n is unfortunately only pseudoeffective, and we want to say something more. So for divisors, the Zariski decomposition, in the Zariski decomposition, the movable part is supposed to capture all the sections of alpha in an asymptotic sense. So with the further property that the mobility of alpha is equal to the mobility of p, where what is this? Mobility is a measure, is an analog, a cycle analog of volumes of Cartier divisors. So this was a function introduced and studied by Brian. So he shows that this mobility function can be defined on nkx to R, and its positivity characterizes the interior of the pseudoeffective cone. So in this sense, it's an analog of the volume function for Cartier divisors, where you have the same property. I don't want to give the definition. It's an asymptotic measure of incidence to points on X. So you want multiples of alpha to pass through more and more general points of X. Okay, and in the case of divisors, we can show that this decomposition is unique, and it coincides with the Nakayama decomposition that John spoke about. And that seems to have some important consequences, or nice consequences, for volumes of divisors. And it's interesting in that case that we allow n to be pseudo-effective, and we show that it's actually effective for divisors, but we don't know what to do for higher codimensions. Okay, I guess I'll stop here.